Good morning. Okay, so we are just going to be going through all of these exercises. We're doing every single one. I'm not playing around. This is going to take a while. We are going to lock in and we're going to do it. Okay, so for exercises 1 through 2, so just for context, what we're studying is linear systems, which is basically differential equations of this form. Y prime is equal to some matrix A times Y. Okay, but we can just get into it. So let me just set up. Okay, so let's just bring it in a little bit more. Chapter 3, equations review. Okay, so what are the eigenvalues? So eigenvals, so problem 1, find the eigenvals of 1, 0, 0, 2. So remember, we just always go back to the definition of what an eigenvalue is. If we have some matrix A, then A times some matrix is equal to some scalar lambda times the vector. So A times a vector is equal to some lambda times a vector. So one thing we could do is we could just look at this. Well, okay, I know the answer. So it's going to be A minus lambda I, because if you turn this into AX is equal to lambda IX, then you get this diagonal matrix that has lambda on the diagonals. And you can then move this over so you get AX minus lambda IX is equal to 0. Anyways, you can factor out the X, and you find that basically the solutions, the values of lambda that give this a non-trivial null space, so X has to be non-zero, are going to be those vectors that we call eigenvectors. Okay. If we say I looks like this, or lambda I looks like this, okay, then we can form this matrix, A minus lambda I. So this is going to be 1 minus lambda, 0, 0, 2 minus lambda. Okay? X is equal to 0. So one thing that's useful in this scenario in particular is that when the determinant of A, or some arbitrary matrix A, is equal to 0, it's not invertible, but also has non-trivial null space. So if we solve for the values of lambda that give us a 0 determinant, then we know that those are the lambdas that give us a non-trivial null space, which allows us to find these vectors. Okay, so what we can do is now take det of A minus lambda I. And this is going to be equal to, if we have A, B, C, D, it's AD minus BC. So we're going to get 1 minus lambda, 2 minus lambda, and then this other off diagonal 0 is equal to 0. So clearly, we're going to get lambda equals 1 and lambda equals 2 for these values that cause the determinant to go to 0. This also has a name, just in case you need to remember that. It's called a characteristic polynomial or characteristic equation of the matrix A, and for a 2 by 2. And then now that we have that, I think that's the whole problem. That's just find the eigenvalues. Okay, so that's problem 1. Problem 2 is find the eigenvalues of B equal to 0, 1, 2, 0. So again, we form b minus lambda I, and we're going to get minus lambda 1, 2, minus lambda. Okay, the determinant of this is going to be lambda squared minus 2. So we're going to get lambda squared plus square root 2, or lambda plus square root of 2, lambda minus square root of 2. So then lambda equal to plus minus square root of 2 is the eigenvalues. So that one's pretty quick. Okay, now problem 3, general solution. Y prime is equal to 3, 0, 0, minus 2, y. Okay, so this is pretty easy because first off we see that lambda equal to 3 and minus 2 are our eigenvals. So now to find the eigenvectors, what we need to do is we need to basically say so this is going to be lambda 1 and this will be lambda 2. So we're going to compute a minus lambda 1 I, which is equal to 0, 0, 0, and then this is going to be what? Minus 5. Okay, and now we want to solve for the fact that this times x is equal to 0, because we need to find what the null space of this is. So we could alternatively have just computed null of this on a computer or something like that. But what we're going to get is I'm actually a little bit blanking because I know that it's going to be 1, 0, right? Like if we multiply this by, but how do we know that it's not? What we could do is we could do a, so if we call this x and call this y, then we get 0x plus 0y equals 0. Okay, but then we have 0x minus 5y is equal to 0. So this constrains y to be 0, but x is free. So the arbitrary, or the like generalized eigenvector, oh, I think that's the wrong word. I think I'm not supposed to say that. It's going to be x0, or the set of all solutions for the null space. So we can just take that to be like 1, 0, because eigenvectors have the property that if you scale them, they're still an eigenvector. Okay, so now that we have that first, so this is called V1. Now we're going to compute V2, so we're going to compute a minus lambda 2I, and this is going to be 5, 0, 0, 0. Okay, times x. So here we're going to get 0, 1 is V2. Okay, now the point, one thing to always remember is if we have two distinct real eigenvalues for a 2x2 system, then we're going to have two straight lines of solutions, and linear combinations of those solutions are also solutions. Because if you have a solution to a differential equation, then I guess the best way to say it is that the solutions of a linear differential equation like this, linear homogeneous differential equation, form a subspace. Okay, so a subspace of a vector space. So anyways, what that means is that since V1 and V2 are independent, we can take a linear combination of these and get another solution. Or you know what I should say before I say that is that the solution corresponding to this eigenvalue eigenvector pair is going to be e to the 3t. Let's put a parameter in front of it so that we can get any solution on the x-axis times 1, 0. So this is y1 of t. And then y2 of t is going to be the same thing. It's going to be k2 e to the minus 2t 0, 1. So now we can just take since these span our space, R2, we can just take y of t equal to k1 e to the 3. Or here, I'll even say this just to make it simpler. y1 of t plus y2 of t. Now for any initial condition, we can just pick k1 and k2 to be x0 and y0. Now that's not always going to be the case. You're not always going to get a basis that's this nice. Our eigenvectors aren't always going to be orthogonal like that, but in this case they are. Okay, now we're supposed to sketch the phase portrait. Okay, so along this, we're going to get it going outward because we have lambda equal to 3, but then we have a lambda equal to -2 here, so we have a saddle. And we're going to get stuff that goes like this. So that's our phase portrait. All right. All right, so the next problem is, which of the following, okay, problem 4, which are eigenvectors for A equal to 1, 0, 2, 3. Now, I'm actually pretty sure that if you have an upper or lower triangular matrix, then you're guaranteed to have the diagonal be your eigenvalues. And the reason that, I mean, it's easy to see for 2 by 2 systems, because if we take 1 times 3 times 2 times 0, like even if we do A minus lambda I, this off diagonal, B and D are not going to change. So since we have a 0 here, this term goes to 0. Thus, our characteristic polynomial is going to be of the form 1 minus lambda, 3 minus lambda, equal to 0. And thus, lambda equal to 1, 3. So that's that. So we have that. Now let's just form our equations. So we're going to get A minus lambda 1. We're going to get 0, 0, 2, 2. The x is equal to 0. So I don't know if this is how everyone does it, but I like to form the equations, because you can always just expand this matrix vector multiplication into equations. So you get 0x plus 0y equals 0. Okay, that doesn't tell us anything, because to satisfy this, x and y could be literally anything. But then you get 2x plus 2y is equal to 0. So we can do y is equal to minus x, because we just solve for y. And then we can say, well, if we plug in 1 to this for x, then we're going to get 1, and then what's y going to be? Minus 1. So this is going to be one of our eigenvectors. Okay, now for the second one, we're going to get 1, 0. Oh, wait, no. We're going to get minus 2, because it's 1 minus 3. So we're going to get minus 2, 0, 2, 0. So in this case, we have minus 2x equals 0 and 2x equals 0. Now the only way to satisfy this is going to be x equal to 0, but y can be whatever you want, so y is free. So our second eigenvector, so this is v1 and this is v2, it's going to be 0, 1. Okay, so now that we've found those, we'll just switch over to this. So they're asking us, which of the following vectors are eigenvectors? A 0 vector is never an eigenvector, so we can already just discard that. So we had v1 was 1 minus 1. That's a scalar. That's a scalar multiple of it. So y2 is an eigenvector. 1, 1, that is not an eigenvector. 0, 1, that is an eigenvector. This is also an eigenvector because it's minus 4 times v1. And this is not an eigenvector. And you know what, let's duplicate this so we can get the answers when we need them. We'll try to use this as sparingly as possible, but it's always good to check, I think. I think for me, the section that I am going to have to spend the most time on is going to be 3.7 and 3.4. So complex eigenvectors is definitely my weakest point. And then the thing that is probably the deepest section in this whole thing is going to be the trace determinant plane, because it sort of brings the whole picture together. And so we're just probably going to study those 14 pictures again. All right, problem 5. Let's do problem 5. Consider the harmonic oscillator with mass 1, spring constant 5, and damping coefficient B. Find the values of B for which the system is overdamped, underdamped, critically damped, or undamped. Okay, I actually don't know those terms really. Well, overdamped, I think. Okay, so here's our steps to solving this. First, we're gonna write out the second order differential equation. Then we're gonna write a first order differential equation. Then we're gonna write it as a matrix form. And then we are going to find the eigenvalues and eigenvectors in terms of B. Okay, and then we're gonna basically look at the discriminant in the quadratic equation that results in the determinant, in the characteristic polynomial. So let's do that. Okay, so what are we given? We're given that, so the general form is going to be like m y double prime plus b y prime plus k y is equal to 0. So this is the general form, but now what we're given is that m goes to 1, and then k goes to 5. So we're going to get y double prime plus by prime plus 5y is equal to 0. Now we can rewrite this as a first order equation with y prime is equal to the velocity of the harmonic oscillator, and then the derivative of the velocity is the acceleration, which we have v here. So y double prime is the same as v prime. This is the process of converting it to a first order equation. And we just move both of these things over to the other side, and we're going to get minus 5y minus bv, because this is v. Okay, so now if we want to write this as a matrix, we're going to get that y, so if we let y equal to little y and v, then y prime is equal to the matrix 0, 1, minus 5 minus b times y. Okay, I'll be back in a second. I am back. All right. Let's do this thing. Okay, so the question was find values of B where the system overdamped, underdamped, critically damped, and or undamped. Okay, so what it seems to me is that overdamped is going to be a straight line solution. So overdamped probably means that the eigenvalues are real. Underdamped probably means that we get oscillations. Critically damped, I don't know what critically damped is. And then undamped would mean B is 0, and we have a center. Okay, so let's compute the eigenvalues. So 0 minus lambda, 1 minus 5 minus B minus lambda. So then we get the determinant of this is equal to minus lambda times minus B minus lambda plus 5 is equal to 0. So if we expand it out, we get lambda squared plus B lambda plus 5 is equal to 0. Now we can use the quadratic formula. So we're going to get lambda is equal to minus B plus or minus the square root of B squared minus 4C, which is going to be 20. A is 1 over 2. Okay. Now, the most important part here is if B squared is greater than or equal to is greater than 20, then we get two real distinct lambda. So this is overdamped. Now if B squared is less than 20, under. And then critically damped, I don't actually know what critically damped means. Let's look that up. Oh, what does that mean? Critically damped is where we have critically damped is where we have only one eigenvalue. Okay. So critical when we only have one lambda, one V. So this is where B squared equals 20. And then undamped is when B squared or just B equals 0. And when B equals 0, we have only complex eigenvalues. So only complex. And it comes in a conjugate pair. Okay, let's check our answer actually. So this is the review exercises. Okay, so overdamped B greater than root 20. Critically damped B equal to root 20. Overdamped and b equal to 0. Okay, cool. Compute the equilibrium points for this system. Okay. So if we have y prime is equal to 0, 0, 1 minus 1 times y. We're doing problem 6. Find equilibrium points. So 1, for any linear homogeneous system or eq, 0, 0 is an equilibrium point. This follows from linear homogeneous solutions are a vector subspace. If it's which was proven, elsewhere. Okay, then the other points must satisfy for y not equal to 0, a y equal to 0, i.e. null of a. Okay, so if we to define the null space, we can do okay, so wait, we're gonna get our equations are 0x plus 0y equals 0, and then x minus y is equal to 0. So then we get y equal to x. So if we plug in 1, 1, then if we do a 0, 0, 1 minus 1 times 1, 1, we're going to get 0, 1 minus 0, 1 equals 0. Okay, so then this, so anything that lies, so let's call this V1, in span of V1 is an equilibrium point. Very good. Oh, okay, solve the initial value problem. They give you this real complex looking thing, and then it's like, oh, but the initial condition is 0. So then this is 0, so it's already at equilibrium. Oh, but you know what? We should actually practice this, just how to write it. Because some professors, like mine, are very persnickety. So if we have y of if we have y prime is equal to ay with y 0 equal to 0, 0, solve IVP. Then we can just say y of t is equal to 0, 0, for all t. Okay, that's how I would write it. And then I would say y is an equilibrium solution. Okay, that's pretty good. Problem 8. For each function y of t, determine if it is a solution to the second order equation Okay, so For each y of t, determine if it is a solution to y double prime plus ky equals 0. All right. Okay, so the first one is y of t is equal to k sine kt for k less than 0. Okay, so the first thing we can do is we can say y double prime is equal to minus ky. Now we can find y double prime. So y prime is going to be equal to k cos kt. And then y double prime is going to be equal to k squared cos minus k squared sine kt. Okay, then we say is k squared sine kt equal to minus k sine kt, and it's not. So it's not a solution. And I'm just going to double check that because okay, so yes. I guess one thing we could say maybe is if k equal to 0 or 1, but neither of those cases, let's see, hold on, we get rid of that, we get k sine kt is equal to sine kt if we cancel. And yeah, but we had the constraint that k is less than 0, so then that's that. So now let's do part B. So B says y of t is equal to 0. So y double prime, so we're trying to figure out if our y of t's are solutions to this second order differential equation, which is the undamped harmonic oscillator. So y double prime is going to be 0, and then k times 0 is also 0, so this is a solution. And we should already know that because we know that the first order system here is a linear homogeneous differential equation, and we know that 0 is always a solution to the linear homogeneous differential equation. All right. Problems part C. Y of t. We have k is less than 0. Okay, so there's no solutions. All right. C is y is equal to t squared. So y prime is going to be 2t. Y double prime is going to be 2. So now we're trying to check that 2 is equal to minus k t squared. And it's not. So it's not a solution. Okay. Now we're going to do part D. D is, oh, this is complicated. Okay, y of t is equal to sine square root kt plus 2 cos square root kt for k greater than 0. Okay, so let's figure this one out. This one's a little bit trickier. So y prime is going to be equal to root k cos k root kt. And then it's going to be plus minus 2 root k sine k root kt. And then y double prime is going to be equal to minus k sine root kt minus 2k cos root kt. What? By the way, I am watching chat. I didn't? How did I not differentiate correctly? Are you sure? I'm pretty sure I did. So anyways, then to figure out if we solve the equation, we get y double prime is equal to minus ky. And we can see that we can factor out a minus k from here. So we get minus ky is equal to minus ky. So this indeed, so we say yes, y of t is a solution to the differential equation, y double prime equals minus ky. Okay, problem E. E is y of t is equal to e to the kt for k greater than 0. Okay, so y prime is equal to ke to the kt. Y double prime is going to be equal to k squared e to the kt. And now we just check, is k squared e to the kt equal to minus ke to the kt? And it's not. We get k e to the kt is equal to minus e to the kt. If k is greater than 0, then this is impossible because this is negative and this is positive. This is going to be positive for all t, and this is going to be negative for all t. So no, not a solution. Okay. Let me just rewrite everything. Hold on, I have to move my camera back slightly. Okay, so now we have chapter 3DE. Okay, and we're doing problem, 8? We're doing problem 8, and it's, is y of t a solution to y double prime equal to minus ky? And now we're doing part F. This is the last part. Y of t is equal to e, here, I'll write it as x square root minus kt for k less than 0. Oh, this one's a little bit harder. We need to take the derivative of this. So if just to recall from calculus, the chain rule, if we're trying to take f of g of x, the derivative of this we can think of as df dg times dg dx. So we can take is equal to f prime of g of x times g prime of x. So this is just rederiving the chain rule. It's always helpful to understand the chain rule in its, in this way, so that you can always just recognize, oh, this is a chain rule. All right. So in this case, for y of t, we're going to get that f is equal to e to the, or here we'll say f of x equals e to the x. And then g of x is equal to square root minus k x. Okay, so f prime is equal to f. It's just e to the x, so that doesn't change. But what changes is this. Oh, I guess in this case with just a pure x, but it doesn't. We don't really need the chain rule, but I like making sure that this is right. So if we have minus k x to the 1/2, I mean, even this is a little nested, but the derivative of this is going to be, if we had, then h prime is equal to minus k. So this is going to go to g prime, which is 1 over 2 minus kx to the 1/2 times minus k. So we should get minus k over 2, or minus, no, minus kx to the 1/2. All right, so this is g prime. All right, so now that we have g prime, we can do the derivative. Wait, hold on. So g prime, this, the derivative of this, I think, is this. Ignore this part. Minus k over 2 times minus kx to the 1/2. Because it's going to be g prime of h of x times h prime of x. And h prime is... Yeah, but what about the square root? Oh, I see what you're saying. Yeah, that's true. That is true. You can do that. So then it would be just... so then you would get... you get square root minus k x minus square root minus kt. Is that what you get? Yeah, you're definitely right. But okay, wait. So we have g prime of x, f prime. So this is just going to be... Oh, but you still have to do the square root part. So this is not the derivative. So I think it's going to be minus k over... It's going to be... So this is g prime. So we're going to get 2 minus kx to the 1/2 times e to the square root minus kt. I think that this is the expression. Let's just double check though. So we have this. So let's just go, oh wait, we already have our thing up. So it's going to be d of x of minus, or square root minus kt respect to t. Okay, it looks like I was right. All right, so I did do it right. Oh, I put an x instead of a t. But besides that, we did do the derivative correctly. Oh no, but we need to do the derivative. We need to do the derivative again. We need to take the derivative of this again. Oh god. Okay. Should we do that? It's so tedious. Because now we got to do this chain rule, product rule. Let's just see how nasty it gets on this. Bro, yeah, I didn't want to do all that. That's a nasty one. All right, should we just do it just so that I'm not like lame? Wait, I'm gonna move this here, move this here, move this there. Okay. Okay, so we need to, so if we take this as A, we'll take this as A1, A2, then this is gonna be B. So actually maybe this is not gonna be so bad. So we need to do basically a prime b plus b prime a. And then we just need to compute a prime. So, you know, I haven't derived the quotient rule in a while, so maybe we should do that. Okay, so the quotient rule is the derivative of, you know, a1 over a2 prime. And what we can do is we can think of this as equal to a1 times a2 to the minus 1, the inverse, prime. So now we can do the product rule, which is going to be equal to a1 prime a2 inverse plus a1 times a2 inverse prime. Now, a1 inverse prime is going to be this is going to be minus a2 to the minus 2, right? No, wait, hold on. Is that right? If we have x to the minus 1, and we take d, I think it is. I think it's, yeah. So then we're going to get, why does this seem wrong? Oh, you know why? Here's where the mistake was made. If you have g inverse prime needs a chain rule on it, so that's where the mistake was made, because this becomes minus. So if we think of this, we have g of x is equal to, or g inverse of x. Let's say h of x is equal to x to the minus 1. Then we have g of x is equal to some expression. You know, I don't know what it is. It could be anything. But the point is that we have this nesting of h of g of x, and we need to take the derivative of that. So we need to get h prime of g of x, and then we need to take, and then we need to do times g prime of x. So what we get is this is going to be minus 1 over g. Well, it's really going to be minus g to the minus 2, right? Because that's just this thing. Then we're going to get yeah. It's, yeah. I know. Anyway, so g prime itself is just g prime. So then we finally get, you know, so the whole thing becomes, you know, f prime g inverse plus f g prime but now the question is, why is it all over g squared and not just this one? Because it seems like it would just be this, but I know it's not. Wait, actually, I think it might be. Yeah, because then don't you do g squared, and then this becomes equal to f prime g plus f g prime over g squared. All right, okay, so we did it. That's actually true. All right, so we write it as a single fraction. All right, so I like deriving it personally. I think it makes more sense that way. So now we need to go back to where we were, which was taking the derivative. So what we're trying to do is we're trying to take the derivative of minus k over 2 times minus kt to the 1/2. And now f prime, so this is f, and this is g. And now f prime is 0. F prime equals 0. So we can just ignore this first term. And we're just going to get f g prime. So we need to take g prime. So if g equals minus 2 square root minus kt, the derivative of this is going to be g is equal to minus 2 minus kt to the 1/2. So this should be minus 1 over kt. So this is g prime. Minus 1 over the square root of minus k, over the square root of minus kt. So now that we have g prime, we should get minus k, oh, but then these cancel, so we're going to get k over square root minus kt, and then this is all divided by so we're going to get multiplied by g squared. This is divided by so we're going to get g squared is equal to 2 minus kt 1/2. So this is equal to 4 minus 4 kt, right? So then we're going to divide by minus 4 kt. And I think it might be just k over minus 4, or we can do the minus here. Kt root minus kt. Okay, so this is equal to a prime. Let me double check that, because that's pretty nasty integral. So we're trying to take the derivative of, here, I can put it here. This is going to be minus k divided by 2 minus 2 times minus, square root minus kt. And we want to do dxt. Where's the k squared come from? Wait, where does the... Oh, I did the derivative wrong, dude. Where did I mess up? Okay, so let's just go step by step. So, if this is g, so we did get minus k, g prime is minus. Oh, because I forgot to. This is a minus k. So then this. What is this? I'm lost. Where were we? So we have g prime. So we just need times f, right? So g prime times f. What is f? F is minus k. So we should get f g prime is equal to k squared over square root minus kt. And now we just need to divide this by g squared. Divided by 4kt. Which is equal to k squared over square root minus kt times 1 over 4kt. Equal to, dude, that they threw in like a really ridiculously hard one at the end. Like, why did they do this? K squared over, I don't know why don't we just cancel this? We could, right? But I guess it doesn't make it that much simpler. So k squared over 4 Mathematica gives me minus kt to the 3 halves. Okay, now we have to do the product rule of this with that. All right, I'm done with this problem, bro. Let's just use the computer to solve this problem. I'm just going to use a computer. Okay, so we have, so this is the thing. So we take this and we check whether or not it's equal to minus k y. So let's let y equal this. And we say d of y, the second derivative of y with respect to t is equal to minus y ky. And then we just call full simplify on it. So it's not a solution. Maybe for, because if k is greater than, I think there is a way to put assumptions in this system, but we're given that k is less than 0. So this is positive, this is positive, this is negative. I think there's no solutions. I think it's not a solution. So let's check. This is 8f. Oh, it says yes. Oh, because it misread it. It misread it. Here, hold on. I'm going to be back in a second. Wait, actually, did I misread the problem? No, the t is definitely in the square root. So hold on. F is actually x of square root minus kt with t in square root. Yeah, it's not a solution. Dude, that's a nasty, nasty... Oh, but you know what? This might be a smart way to do it. Instead of actually having to take the derivative. Oh, no, they do take the derivative. Oh, that's smart. Actually, do a u sub or something like that. How did they do this? They said... Then u prime... Is that true? That the derivative of square root of 3x... Is this correct? This doesn't seem right. So then you get... you get 1 over 2 times square root 3x times 3. Oh, because... Okay, they simplified this. All right, that makes sense. So then you get square root of 3 over 2 root t, or x. Then you get u double prime. Then you take y prime. Okay, so then we have u double prime is equal to the derivative of, yeah, root m over 2 root t. And the root m over 2 is just a constant, so we just need to take the derivative of 1 over root t, which is equal to t to the minus 1/2, which should be equal to minus 1 over 2 t to the minus 3, or 2t to the 3 halves, times root m over 2. That's going to be minus root m over 4 t to the 3 halves. Okay, so you have u double prime. Then y prime is equal to, since y equals e to the u, then y prime equals u prime e to the u, and y double prime equals, we have to do a product rule, right? So we have u double prime e to the u plus u prime times e to the u prime, which is u prime again e to the u. So we get u double prime. Oh no, this is a squared. Yeah, this is a squared. So we get u double prime plus u prime squared times e to the u is equal to y double prime. Okay, hey, it was great having you here, bro. Subscribe, man. I do a ton of math stuff. This derivative really got me hung up. Yeah, let's see where we're at. So that's where we're at. So the point now is that you can now that we have y double prime, we can substitute this in. So we get u double prime plus u prime squared times e to the u is equal to minus k times y, which is y is equal to e to the u. And so then we can replace this as e to the root mt minus, right? Or we did the sign change. Okay, that's fine. Times minus root m over 4t to the 3 halves plus u prime, which is u prime is this. So u prime is root m over 2 root t squared. So then this becomes m over 4t. Oh yeah, and we replace this with m. So we get, oh yeah, and we can factor this. Oh, this is smart, bro. This is smart. Yeah, dude, I have an exam on Tuesday. And so, and the thing is, this is the type of professor that, like, you just never know. Like, his homeworks are easy, and really there's, like, 2 problems of homework, and then his tests are, like, crazy hard. So, that's just where we're at with this class. Okay, wait, we need to factor this. So, what actually happens is we can do e double prime, u double prime, plus u prime squared. And then this is going to be, yeah, minus m e to the u, because we move this to the other side. And we can actually just factor this whole thing. Oh, this is u. So we get e to the u double prime plus u prime squared minus m is equal to 0. So now it's all about whether or not we can satisfy this equation, which if we expand it out is minus root m over 4t to the 3 halves plus m over 4t minus m is equal to 0. So we get this quadratic equation, kind of. And so now all we need to do to verify whether or not this is a solution to the differential equation or not is if there are any values that are non-zero here. Because for all t, this needs to be 0, otherwise it doesn't satisfy it as a solution to the differential equation. So if we take t equal to 1, we're going to get like minus root m over 4 plus m over 4 minus m, where m is equal to minus k. So for not, okay, so therefore, e to the square root minus kt, not a solution. Finally done with that one. That one was a nasty problem, man. Okay, problem 9. Find a linear system for which the function y of t equals to 3. Find a linear system for which the function y of t. Okay, so find system where y of t equal to 3 cos 2t sine 2t is a solution. So we need to figure out so if we just take the derivative of this, we're going to get minus, so y prime, let's switch over, y prime is equal to minus 6 sine 2t 2 cos 2t. Now we need to find an a such that y prime is equal to a times y. So if we just had a, b, c, d times 3 cos 2t sine 2t is equal to minus 6 cos sine 2t 2 cos 2t. We would get a system of equations, right? So 3a cos 2t plus b sine 2t is equal to minus 6 sine 2t, and then 3c cos 2t plus d sine 2t is equal to so we solve and we get b is equal to minus 6, a is equal to 0, c is equal to 2/3, and d is equal to 0. So our matrix should be 0, minus 6, 2/3, 0. Let's check our answer. Zero minus 6, 2/3, 0. Nice. That one was pretty easy. Okay. So we need to find the general solution. General solution y prime is equal to 0, 0, 0, 1, 0, 0, 1. Sketch phase. Okay, so the first thing we want to do is we want to do find, so step 1, find the eigenvalues. So we're going to get, for a minus lambda I, we're going to get minus lambda 1, 0, minus lambda. And the determinant of this, det, is equal to lambda squared minus 1 is equal to 0. So we get lambda is equal to plus or minus 1. So for lambda 1, we're going to get equal to 1. We're going to get a minus I is equal to minus 1, 1, 0, minus 1. So we're going to get minus x plus y is equal to 0, and minus y is equal to 0. So this means that x only 0, so this is not. All right. So the next step is then finding for lambda 2 equal to minus 1, we're going to get 1, 1, 0, 1. But isn't this... So this thing has no eigenvectors. I feel like that's not true, though. Because 0, 1, 0, 0 times... Oh, that's actually true. Because if we did 0, 1, we'd get 0, 0 plus. So this thing has no eigenvectors. This is a good problem. So what is the general solution? The general solution... Well, okay, let's just try to plot some of the phase portrait. If the at 0, 1, we have 1, 0. So this thing is going to be pointing this way. So I definitely computed this wrong because I almost know that 1, 0 is equal to v is an eigenvector, but how did this mess up so badly? Oh, because this determinant is not, bro. Because this determinant is not that. It's lambda squared equals 0, so lambda equals 0. So we have a repeated eigenvalue. But you gotta be careful. So this is all bad. Okay, so in that case, we want to solve for this. We want to do this because we want a minus 0 0 x is equal to 0. So we get v1 is, so this okay, so what we're going to get is this and then here this is going to be like that. And then so the general solution is going to be so if we have a it should just be okay, wait. This is actually a really good problem because we have a repeated eigenvalue. And we have a line of equilibrium solutions on the x-axis. But all of these are going to move at a constant rate. So just to construct it without doing all the extra, the like correct way of doing it, it should be like y of t is equal to t times 0y0. Oh, wait. T times y0 is 0. But we need to remember, so there's this procedure that when you have we need to remember this. How do you do it? Let me look at my all right, come on, let's just think about it. So then you find like the generalized Oh, wait. No. You solve a minus 0I times w equal to v. Zero, 1. In this case, it was the same. How does my book do it? Mm-hmm. Right, okay. We definitely should do a couple of practices on that. Like, I don't know if it's going to show up on the test, but definitely want to. Then we study the solution closely to see if there's any pattern that can be generalized. We separate the terms. You get lambda e to the lambda t v0. Okay. E to the lambda t, lambda plus the right-hand side. Okay, I'm going to write this whole chain out again. So in the book's way, we guess this thing. Then we verify that like y prime is going to be equal to lambda e to the lambda t v0 plus e to the lambda t v1 plus lambda t e to the lambda t v1. Now you can factor e to the lambda t times lambda v0 plus v1 plus t lambda t e to the lambda t times lambda v1. Then a times y of t is equal to a of e to the lambda t v0 plus te to the lambda t v1, which is equal to e to the lambda t a v0 plus te to the lambda t a v1. Now these are both equal. So we get e to the lambda t lambda v0 plus v1 is equal to e to the lambda t a v0. So these cancel. And we also get te to the lambda t lambda v1 is equal to te to the lambda t. Here, I'll put it on the screen. To the lambda t a v1. So, since a v1 is equal to lambda v1, so this is 2 and this is 1, from 2, v1 is an eigenvector. Or 0. And 1 says a v0 is equal to lambda v0 plus v1. So v1 is equal to okay, this is actually a nice way to do it. So you just remember this. It's not that hard to memorize, but you memorize this. And you don't even have to remember that v1 is an eigenvector. You just remember that for repeated eigenvalue 2x2 system, that is the general solution. All right, so we can now go back to number 10. So number 10, So number 10, we had A is equal to 0, 1, 0, 0, lambda equal to 0, repeated. Then we found that V1, the actual eigenvector, is equal to 1, 0. So now we just remember that our general solution is going to be y of t is equal to e to the lambda t, so this is going to be e to the 0 t, times v, let's just call this v. So wait, what is the chain of logic that we need to go through? We just call this v0 and v1. And we derive that y prime is equal to e to the lambda e to the lambda t v0 plus e to the lambda t v1 plus t e to, and then we get is equal to a times and then we get, I'm just doing the exact same thing we did just so that I remember it. So then we get we're going to get e to the lambda t times lambda v0 plus this is going to be equal to this, which is equal to e to the lambda t a v0 plus t e to the lambda t a v1. So we get our two equations are AV1. Okay, so this is going to be our eigenvectors. So this is going to be, so our general solution for 10 is y of t is equal to e to the lambda t v0 plus te to the lambda t 1, 0. Now we just need to find v1. And we find v0. Now to find v0, we solve a v0 is equal to lambda v0 plus v1 for v0. And the way we're going to do that is we're going to say v1 is equal to a minus a v0 minus lambda v0, which is equal to a minus lambda I v0 is equal to v1. So this equation becomes, so a minus lambda I, since lambda is 0, we're going to get just a, so we're going to get 0, 1, 0, 0 times x, y is equal to 1, 0. So we're going to get y is equal to 1, and then x equal to 0. Oh wait, isn't x free? Hold on, is x free or not? No, because we have 0x plus 0y is equal to 0. So it has to be 0. So then we get 0, 1. is equal to v0. So then our general solution is going to be y of t is equal to e to the lambda t times 0, 1 plus te to the lambda t 1, 0. I think that's the general solution. Those problems are tricky, man. The sketch is easy, but I do for some reason have trouble with the repeated root ones. I don't know why. The repeated root ones and the complex ones. Yeah, so I got this. This was easy. Actually, let's go back to this and just think about it. So this is equal to, so this goes to 0, 1. So then we have 0, 1 plus t. Oh, wait, but we have k1, k2. But v0 is supposed to be the initial condition. Hold on, I'll be back. Bro, yeah, this is like actually one of the craziest parts of the chapter in a hidden way. Like they don't really even like, yeah, this Kaylee Hamilton stuff is nuts. So instead, what we need to do is so instead the steps are um, you take you find lambda, then compute, then compute for arbitrary x0, y0, a minus lambda I times x0, y0. And then we say that's v1. Then we just know, then you remember repeated roots have solutions. Y of t is equal to, this is v0, e to the lambda t v0 plus t e to the lambda t v1. So maybe you just, that's not that complicated, but for some reason this is like the hardest thing to remember. All right, so let's do problem 10 again. We have y prime is equal to 0, 1, 0, 0 times y. Find general solution. Okay, so step 1, find lambda. Minus lambda squared is equal to 0, so lambda equals 0. Step 2, compute 0, 1, 0, 0 times x0, y0, which is equal to y0 this is equal to v1, and this is v0. Then we just say y of t equals v0, which is x0, y0, plus te, or wait, this goes to 1, times y0, 0. So this is the general solution. Okay, that's not so bad. All right, true, false. I like true, falses. The origin is the only equilibrium point for any linear system. That's false. Oh, we'll give a counterexample. The counterexample is when a non-trivial. I'll just say when a is singular. A singular. Not zero determinant, non-zero null space, that kind of thing. All right, 12. If y0 is an eigenvector. If y0 is an eigenvector for a matrix, then so is any non-zero scalar multiple of y. True. Because if we have a y0 equal to lambda y0, then we say y1 equals, or let's just say y is equal to k y0. Then we have a of k y0 is equal to lambda k y0. Then we get k a y0 is equal to k lambda y0 is equal to k lambda y0. $13. Is not a solution to any linear system. Y of t is equal to minus 2 sine 2t, and then cos t. Oh wait, why did I take the derivative? Shit, hold on. Y of t is equal to cos 2t sine t. Y prime is equal to minus 2 sine 2t cos t. Y double prime is equal to minus 4 cos 2t minus sine t. Wait, why am I taking the second derivative? Bro, I'm like in a robotic mode right now. So we do A, B, C, D. Some arbitrary matrix A times y cos 2t sine t is equal to minus 2 sine 2t cos t. So then we get, oh, actually, I think that might be true. Because here, look at this. We're going to have A cos 2t plus B sine t is equal to minus 2 sine 2t. But there's no way to satisfy this. And then you get C cos 2t plus D sine t is equal to cos t. And here, there's no way to match these frequencies. So 13 is true. Therefore, no linear system satisfies y prime is equal to ay. Cool. That's a good problem, actually. I really like that one. This is a good problem. 13. Because we did... not that one. We did... Didn't we do a cos thing? Oh, I think it was this one. That's why I probably took the second... Oh, no, here. Find a linear system. But see, in this case, the frequencies are the same. But if the frequencies aren't the same, then we can't. So 14 is true. All right, or 13. 14, the graph on the right is the graph of the solution of a damped harmonic oscillator. I don't think so. That doesn't look right to me at all. All right, 14, false. Because, wait, this is the position with respect to time. There shouldn't be a lag here. That doesn't make any sense why there would be a lag there. Okay, problem 15. The graph on the right is the graph of a typical solution of a damped harmonic oscillator. Yeah, that looks right. Because it kind of starts decaying. Problem 16. If K increases, then the time between successive maxima of solutions. Oh, this is a good problem. I don't know. We need to think about it. All right, here, let me show you guys what I came up with for 16. So, all right, so what you do, so you take, so I figured out that the solution, that a solution is going to be y of t is equal to sine square root kt. Okay, because you can verify that this indeed is a solution to the differential equation y double prime is equal to minus ky. But the thing here is that as k increases, so we're trying to figure out where sine, how, so we want, I guess we want to solve square root of k times t is equal to 2 pi. So we get t is equal to 2 pi over square root k. So as k increases, Yeah, t decreases. I think this is true. So this is 16 true. We're going to double check all these answers, but I'm pretty sure that that's actually true. Because the frequency goes up and the period goes down. All right, 17. Suppose A is a 2 by 2 matrix. The linear system can have 3 different straight line solutions. That is true. That is true. But the only case in which that's really true is when every initial condition is a straight line solution. Yeah, I do want to do a review of finite time blowups, because finite time blowups are the craziest thing. It's like, how does that even happen? But I'm pretty sure that that is true. Because how could it? All right, so let's double check. Okay, so where is our solutions? 11 is false. 12 is true. 13 is true. 14 is false. Why did they say it? They said 15 is true. 16 true. And then 17 is false. I said true. 17 is true. Consider 2 times I equal to A. Every initial condition, every point is an eigenvector. Oh, wait, but different? I guess the word different is and then 18 is true. Okay, very good. Easy. Wait, problem 19. Ooh, I like these. I like these. These are fun. Okay, so what do we expect this one to be? Okay, so actually, the best way to do these ones is the best way to do these ones is to do trace determinant. So the trace of this one is 0 and the determinant is -1. Okay, so let's just use I. T equals 0, D equals -1 plus 2 equals 1. So the determinant is positive. So we're going to have complex. Okay, so the eigenvalues of this system are going to be purely complex because T is 0. That means that it's a center, but I don't know if a center can be ellipsoidal like that. I'm pretty sure it can. So 1 could be A. I don't know how we figure that out, but 1 could be A. Could be A. It definitely is the case that trajectories that are ellipsoidal but like perfectly periodic must have 0 real part, because if they have any real part, then they're gonna start to decay or expand. Okay, so that's a candidate. If we see another center, so this is a center, then we'll have to like do some more analysis. For 2, we have trace is equal to -2 and determinant is equal to, well, since the trace, okay, it's going to be -3 plus 1. -3 plus 1 is equal to -2. So t squared minus 4, we're going to have, so t plus or minus square root of t squared minus 4d over 2. This is going to be positive no matter what. Or wait, we're going to have 1, it's going to be -2 plus or minus the square root of 4 plus 8 over 2. So this is going to be 2 root 3. So we're going to have a saddle. So this is a saddle. So this is a sink with, this is a sink, so that's not that. This is a saddle, so it could be C. Could be C. Okay, 3. We're going to get T equals -3 and D is equal to 1. So then we're going to get -3 plus or minus square root of 9 minus 1 over 2 is equal to -3 plus or minus 2 root 3, or 2 root 2 over 2. So we're going to get, is that a saddle? No, I think they're both negative, because how do you see that minus 3 is going to be greater, or 3 is greater than 2 root 3? You have to be able to see that. But is that true? I'm almost positive it's true, because the reason why it's true is that if you square it, you get 8, and 8 is less than 9. So that means that we're going to have 2 negative, so 2 negative real eigenvalues. So this is a sink. Okay, so we got a sink for 3. So that means that it could be B, so it could be B. All right, now we do IV. All right, 4, we're going to get trace 0, determinant minus 1 minus, or minus 1 plus 2 is equal to 1. So we're going to have, so this is also a center. If the trace, wait, hold on. If the trace is 0 and the determinant is negative, then we get a saddle. But the determinant is positive, so we have a center. So it could be A. So now we need to do some work to figure that out. This is also a saddle. So I guess we need to find the... You should do this exercise without using technology. That's right. Okay. Wait, actually, let's continue with IV. So we found that maybe we can evaluate at, so A for 4 is minus 1, 1, minus 2, 1. And if we just plug in 1, 0, we're going to get minus 1, minus 2 as our vector. So at 1, 0, minus 1, minus 2. So this is going that way. Now let's go to this one, 19. 1, 1, minus 2, minus 1 times 1, 0. So we're basically just trying to do another check to see which whether it's going clockwise or counterclockwise. And this is going to be equal to 1 minus 2. So A, so this can't be A. Not A, because the arrow at 1, 1, 0 is wrong. Because for this matrix, at 1, 0, which is like maybe like right here, we have a positive x, so it'd be going out here. So I think that one has an ellipse that looks like this, not this. So, but this does look like minus 1, minus 2. So A, so I would say 4 is likely A. All right, now we need to do 5. So 5 is a saddle because it's upper triangular, or it's lower triangular. So its eigenvalues are the diagonal. So we have lambda equals 2 and minus 1. But since we already had a saddle, we need to figure out what the eigenvectors are, right? This is our sink, right? B is a sink. Okay, so here we have a saddle for 5, right? So we need to figure out what the eigenvectors are. We have 2, 0, 1, minus 1. With lambda equals 2 minus 1. So we're going to get 0, 0, 1, minus 3. So x is equal to minus 3y, or plus minus 3y is equal to 0. So y is equal to 1/3 x. So if x equals 3, we have a 3. 1 is our first eigenvector. And then the second eigenvector, we're going to get 3, 0, 1, 0. So then we just have x equals 0, y free. So 0, 1 is the second eigenvector. So 3, okay, so wait. This is a saddle. This is a saddle. But this is not the right, so this can't be C. So 5 is nothing. What is this one? This one is, this is a repeated root. All right, so we got our repeated root here. Okay, so number 6, what is that, VI? Okay, we have trace is 3, determinant is 1. So trace is 0. No, trace is 3, determinant is, so this is a saddle, right? Yeah, this is a saddle. Oh, wait, no, determinant is 1. Trace 3, determinant 1. Ooh, we need to look at the discriminant. So we're going to get 3 squared minus 4 is greater than 0. So then we have, so this is a, okay, wait, hold on. 3 plus or minus the square root of 5. Over 2. So this is going to be just a source. This is just a plain old source. And I don't think we have any sources here. So this is nothing. So VII. Okay, here we have trace equals minus 4, determinant equals 4. So minus 4 plus or minus the square root of 16 minus 6. So here we have a repeated root, right? Minus 16 over 2. So we're going to get repeated root at lambda equals minus 2. So now if we compute, so we're doing 7. So if we compute a minus 2i, or plus 2i, we get 2, 1, minus 4, minus 2. So then we get 2x is plus y is equal to 0. So then we get y is equal to minus 2x. So then we have our eigenvalue is 1 minus 2. 1 minus 2, that indeed looks like this. So then this is D. So we have, so what do we have so far? We have, what was 2? 2 was, could be C. because it's a saddle. But let's look at the eigenvalues then. So 2 had lambda of -1 plus or minus √3 equal to lambda. So what is A? 2 is A is equal to -3, 1, -1, 1. Ugh, that's a pain in the butt to. Okay, wait. So we'll put a pin in that one because I don't even want to compute the eigenvectors for that one. I mean, we might have to. So, but now number 3, I said it could be B because 3 is a negative sinc, or I mean, is a sinc. So it could be B, but we haven't computed this yet. Let's just look at the trace. So the trace is -2. Okay, so it could be a sinc. The determinant is -3. Okay, wait, let me just do 8. So 8 is trace is equal to -2. Determinant is equal to -3 minus -6. So +6 is equal to 3. So we have so this is going to have an imaginary component to it. So therefore, this is going to be -2 plus or minus the square root of 4 minus 12 over 2. So this is going to be a spiral sinc. So 8, there's no spiral sinks in here. So I think we have our guesses, but I need to go to the bathroom. All right, so our guesses are going to be 2 is a saddle. But I think we already have a good guess for our saddle, don't we? 3, 1, and no. So 5 is a saddle, but its second eigenvector is on the on the y-axis. So, okay, so I'm guessing 2 is C. So for final answers, 2 goes to C. What is 3? 3 is a sink. 3 is a sink. Do we have any other sinks? I don't think so. So I'm going to guess 3 goes to B. Oh, wait, hold on. Yeah, 3 goes to B. 4 goes to A. And 7 goes to D. All right, let's check the answer. So 19, A is 4, B is 3, C is 2, and 7 is D. Nice. Easy, bro. Easy. Okay, chapter 3, D, E. This is going to be 20. Consider A is equal to the matrix 0, 3A, 1A. Okay, the problem is draw the curve. Draw curve in TD plane via varying A. Okay, I'm going to hop over to my... Oh, and then determine the bifurcation values. B, determine bifurcation values. And briefly discuss the types. Yeah, do all the bifurcation stuff. All right, so the first thing we do, trace is equal to A. Determinant is equal to minus 3A. Okay, so if we were to plot the parametric curve A3A, then we should get should we not get something like this? Like if A is 1, then 3A is 3, so we should get something like this. Okay, and then somewhere in here, we're going to have this. I don't know if this is correct, but in terms of its scale or something. But presumably, actually, way up here, this is going to cross this. So maybe we should do a second one like this. We have this. Then we have because this might cross here. So, okay, so let's figure this thing out, right? So we want to solve, so we have t squared is equal to 4d, right? So what we want is t squared equals a squared, and 4d is equal to 12a. Wait, minus 3a, oh shit. So this is really like this. Scratch this one. Okay, so it's minus 3a. So this is good, but this still, so this is going to be minus 12a. So now we're solving for a squared minus plus 12a is equal to 0. So we're going to get a times a plus 12 equals 0. So we solve for, yeah, a equals 0 and a equals minus 12 are the points at which it crosses the repeated root curve. So, and what happens when Okay, so in general, these are the bifurcation values. But the question is, basically, we're going to get a sink to a 0 plus sink. Oh wait, not a 0 plus sink. A repeated sink. Then we're going to go to a spiral sink. Then we're going to go to 2 0 lambda, which means, because this is when A is 0, so this is like 0 0 1 0. So it's not actually like a completely dead system. It's one of those systems that, like, this should look like when y is 0, it's at equilibrium. So these are all equilibrium points. But we're going to have this thing where, like, this one. And then what do we go to after that? We go to a saddle. Cool. Problem 21. Ooh, this is a good problem. All right. Check it out. 8 matrices and 4 pairs of x of t and y of t graphs are solutions to linear systems are given below. For each matrix, form the associated linear system and determine which system corresponds to each pair of graphs. All right, so let's look at the graphs first. Okay, we have a center, we have a spiral center, we have a source, but the thing is, yeah, we have a source, and then now A is the trickiest one because I think A is repeated root, but it could, no, A could be sink. Let me think about that. How would you know if that's a sink or a repeated sink? Or repeated lambda sink? Okay, so wait, so A is either repeated lambda sink or sink. B is a source. C is a center. And D is a spiral center. So then now we just need to do a bunch of calculation of eigenvalues and eigenvectors. So 1's trace is 3, and its determinant is -4. So so 9. Oh, D is, okay, wait, this is a source. Because it's going to be 9 plus or minus, oh, wait, it's going to be 3 plus or minus the square root of 9 plus 12. Oh no, this is trace equals 3 and determinant equals, oh yeah, this is a saddle, and there's no saddles in here. Because what we would expect to see for a saddle is that one of these approaches the 0, or like one of these approaches 0 and the other one goes to infinity. Because that's what a saddle does. So that's not right. Okay, 2, so this is none, so we can discount. Now 2, we're going to have lambda equals 2, lambda equals 5, and then we're going to have trace equals 7, and determinant is equal to 10 minus 0 is equal to 10. So we're going to get 7 plus or minus the square root of 49 minus 40 over 2. So then we're going to get 7 over 2 and 4 over 2. So this is a source. This is a source. So it could be B. We would have to, so let's just finish it, make sure that it's right. So we're doing 2, so A is equal to 2015. So A minus 2I is equal to 0,013. X is plus 3y is equal to 0. Y is equal to minus 1/3 x. So then our eigenvector is going to be 3 minus 1. Okay. Oh, but you know what? That's not going to help us, right? How do we... Okay, well, we computed it. We can think about that later. 3 minus 3 minus 2, 0 minus 1. So we have lambda equals minus 3 minus 1. Then we have trace is equal to minus 4, and determinant is equal to 3. So the trace is negative. Okay, now we need to look at the discriminant. So minus 4 plus or minus the square root of 16 minus 12. So this is a saddle, right? I'm pretty sure this is a saddle because you're going to get minus 4 plus or minus 2 over 2, which is minus 2 over 2 and minus 6 over 2. Wait, it's not a saddle? What am I talking about? This is a sink. Do we have any sinks? We have, so this is potentially A. So maybe A. What was that? Okay. Now let's do 4. Trace 0, determinant is equal to 4. So we have a center. V. We're going to have trace equal to 0, determinant equal to 10. Oh, wait, no. Minus 1. Yeah. Trace minus 1 minus 10 is equal to 9. So we have 9. So then this is also a center. So we need to do more. We need to figure something out. How do we know? Is it by the amplitude? Okay, so wait, let's do 4 again. So 4 is going to be 0 plus or minus the square root of minus 16 over 2, which is equal to plus or minus 4i over 2, which is equal to plus or minus 2i. So these are the lambdas. So then we have e to the 2i is equal to cos 2t plus I sine 2t. So that tells you about the frequency. So you need to look at the frequency then. So at 2 pi, let's see, 1, 2, 3. So wait, it went in 2 pi, it did 3 full cycles. Which means that it's hold on. So what is the period of this? The period looks like, so if we went 6 pi, so then I think the period is, I think the frequency is 3, right? So frequency looks like it's 3. Because if it went 6 pi in 2 pi. All right, so let's figure out so for 5, we have 0 plus or minus the square root of 0 minus 4 times 9, which is 36 over 2. So we're going to get plus or minus 6i over 2 is equal to 3 plus or minus 3i. So the frequency is 3, or the frequency is 3. They call that the natural frequency, right? Not the angular frequency, because sometimes they do it in radians. So then 5 I'm going to say is C. So this is C. Because its frequency lines up. Okay, which ones do we know for sure? We only really know C. I think that 3 could be A. Because it's a sync. I don't know how we're going to get... Oh, you know what we could do? We could find the eigenvectors. If we find the eigenvectors, then that'll probably tell us a little bit more about... Because we know what the initial condition is, so we can maybe figure that out. If it comes to that, though. Because if there's no other... If there's no other sync, then we don't even have to do that. All right, let's look at 6. So 6 is 1, 1/4, 1/4, 1. So the trace is 2, and the determinant is 1 minus 1/16 equal to 15/16. So the trace is 2 and the determinant is 15, 16. So we need to figure out 4 minus 4 times d. T squared. Okay, so we're going to have 2 plus or minus the square root of 4 minus 4 times 15 sixteenths, which is positive. That the discriminant is positive. So that means we're going to get, it's positive and it's slightly, oh, but it's like very small. So we're going to have 2 positives. So this is a source. Oh, shoot. So we have a source on B, but we have number 2 was also a source. So I'm not sure about that. We'll come back to that. Okay, 7. The trace is minus 2.2. So trace is negative, and the determinant is going to be, this is going to be like, I don't know, 1.21 minus 4. So we have, so for 7, we have trace equals minus 2.2, and then the determinant is equal to 1.1 squared plus 4. So this is a spiral sink. So this is a good candidate for what, number 4 for D. So this is a spiral sink. So we have this one, and then 8. The trace is also negative. Ugh, come on, man. Wait. The trace is negative. Trace equals minus 0.2. The determinant is going to be equal to 0.9 times minus 1.1 plus 5. So the determinant is positive. All right, so we need to figure out the discriminant then. So we're going to get, I don't know, like really small number, like almost 0, plus or minus 4 times something that's positive. Oh, wait, minus 4 times something that's positive. So we are going to have an imaginary component. So this is also a spiral sink. However, it decays very slowly. So we need to figure out how, I don't know how you're supposed to do these fast. These problems take a while. I guess we can figure out the frequency. Get so messy. So, all right, what do we have? We have a saddle, which is nothing. So I is nothing. We can just disregard it. We have 2, which is a source. So 2 could be B. 3 is a sink. could be A. I don't think we had any repeated roots. Okay, so it's between, so B is either 2 or 6. A is definitely 3 because there's no other sinks. C is a center and it has frequency 3, so it's 5. And then D is between 4, or not 4, 7 and 8. Okay. So how are we going to determine... Okay, so we know the initial trajectory is in quadrant X positive, Y negative, quadrant 4. Does that tell us anything? Damn, this is a tricky problem. Okay, so at least we can probably figure out D. So okay, so 7 has a pretty slow frequency. Eight, on the other hand, has seven has a frequency of almost 1, and it's gonna be about 0. Oh wait. Okay, I'm going 7 on D. Now the only one is B, but let's just check the answers. Okay, so here A is 4. Oh wait, no. A is 3, yes. B is 6. But I don't know how they knew that. C is 5. Oh, and D is 8. Damn it. How did they do that? How do you know? Yo, what's up? What's going on? Pretty good. Stressed out. I got finals in 2 weeks, but I have my most important test on Tuesday. What about you, bro? What are you up to? Okay, wait, hold on. Yes, we have our wait. Two's trace. Did I get that right? Two's trace was 7, and determinant was 10. Yeah. Discriminant was 9. Yes, but how do we know? Yeah, life's good, bro. Dude, some of these videos have been kind of popping off. Not this one, but like or not really popping off, but the average concurrent viewers for like the Laplace transform and the discrete dynamical system one are doing there's a lot of people in there. I mean, for me, for math streaming content, there was a lot of people in there. Oh. Oh, okay, wait, hold on. We can look at these grow about equally fast. So if we look at the eigenvectors for 2 and 6, Okay, and then D, look at the decay rate. That damps out very quickly. Oh, you look at the damping. Okay, that's what you do. Yeah. Okay, so what you're supposed to do is look at negative at the real part for decay rate, and then you look at the eigenvectors. Yeah, you look at the eigenvectors. I haven't gotten a haircut. I actually really need a haircut. It takes too long to dry. Okay. Problem 22, chapter 3, problem 22. Give an example of a linear system that has an equilibrium solution x of t, y of t. Give an example of a linear system that has an equilibrium solution I don't even know what this thing is asking. Give a linear system that has an equilibrium solution x of t, y of t, where x at 0 is equal to minus 1, and y of t is equal to 2x of t for all t. Give an example of a linear system that has an equilibrium solution where x at 0 is minus 1. Can you not just do x of t equals e to the minus t? Because then if t is 0, or minus e to the minus t. If you gave like x of t is equal to minus e to the minus t, and then y of t would be equal to minus 2e to the minus t, then 0, 0 is an equilibrium solution. Okay, that's my guess for that one. But the But I feel like the solution that I just gave, minus e to the minus t minus 2e to the minus t, has a straight line solution. It has two straight line solutions. I don't even get what this one's asking. This is a tough problem. Oh, yeah. Yeah, do you have crows in Poland? Oh, yeah, you guys have crows. Dude, there's a family of crows that just got born or something, and I was reading about crows, and they're very interesting species. They make like lifelong pair bonds. They do a lot of stuff that humans do. It's kind of interesting. They're social, you know. Is that what that means? Oh. Okay, so one you find. Okay, so the answer to this problem is we're looking for a system where x of 0 equals minus 1 and y of t is equal to 2x of t for all t, and x of t, y of t is an equilibrium solution for any t. So if we have like, okay, so if we have minus 1 minus 2 is equal to y0, then we want our matrix A times y0 to equal 0. So we just need to construct a matrix that has this vector in its null space. So if we do A times minus 1 minus 2 is equal to 0, we're going to get minus A minus 2B is equal to 0, and then minus C minus 2D is equal to 0. So we get A is equal to minus 2, or wait, we're going to get, yeah, A is equal to minus 2B. So if B is 1, then A is minus 2. So we get minus 2, 1, minus 2, 1. Okay, all right, that problem makes sense now. And now this one, this is what I did. That's what I did, but I did it for the wrong problem. Oh, nice. I don't have my phone on me. I turned it off because I got to lock in, but I will look at it later. Okay, that one's fun. Find the solution in scalar form of the initial value problem. See, how many problems do we have? Okay, these are going to be the best ones to do. Then we're going to go through and we're going to review all of the homework problems that got assigned. Yeah, I'd like the crows more if they weren't so dang annoying. They're just so loud. But no, they're cool. Okay. Let's freaking lock in. I don't expect... All right, he always gives 5 problems. There's definitely going to be one about finding the general solution to a complex valued, like a spiral center, or a spiral sink or a spiral source. Let me just try to game out what problems he's going to give. He's definitely going to give general solution to complex. What else could he give? Probably something, let's see, what is in this section? I'm worried he accidentally gives something on like chapter 2. He said chapter 3, but I can totally see him giving something like nonsensical from a different chapter. Okay, there'll probably be... I feel like it's likely that he's going to test Laplace transforms. So there's probably going to be a Laplace question. Because he said it's in the curriculum. He really likes 3.7, so there will probably be some... One of the questions will be... find the bifurcation values for a linear system. Values of linear system and do like one of those plot maybe even the 2-parameter, or probably more likely is a 1-parameter family, which is a lot easier. The 2-parameter problem I had to use Python for. What other things could we get? I could see an analyze a 3x3, a 3x3 system, or a 3-dimensional system, which means we need to find the eigenvalues of a 3x3. But likely whatever 3x3 he gives us will be partially decoupled, so it won't be nearly as hard as like having to compute a full 3x3 determinant, because it's like he's like not totally unreasonable. I could see there being a question about harmonic oscillators. Oh, you know what? There's probably a theory question. About linearity principle. Because if I were a teacher, I would definitely ask these kind of questions. All right. So let's just keep plugging away at this, though. All right. Problem 23. So the question is, find solution in scalar form. Find scalar solution to the IVP. All right, let's hop over to the camera. All right. So, and then we have y of 0 is equal to 0, and y prime of 0 is equal to 2. All right, so to solve the general solution of harmonic oscillator, we want y prime equals v prime equals minus 6y minus 5v, which is equal to 0, 1, minus 6, minus 5. Okay, now we want to find the eigenvalues, so we go 0 minus lambda, 1, minus 6, minus 5, minus lambda. The determinant of this is equal to minus lambda Okay, then we compute a minus plus 2 I is equal to 2, 1, minus 6, minus 3. So we get 2x plus y is equal to 0, y is equal to minus 2x. We get our v1 is equal to 1 minus 2, and then be 2a plus 3I is equal to 3, 1 minus 6 minus 2 is 3x plus y is equal to 0. B2 is 1 minus 3. Okay, so we have our two eigenvalues and eigenvectors. Now we just need to, so now our solution, so we have two distinct things, then our solution y of t can be written as y of t is equal to k1 e to the minus 2t times 1 minus 2 plus k2 e to the minus 3t 1 minus 3. So this is our general solution. But this is the vector form of this solution. So first, the next thing we need to do is we need to figure out what k1 and k2 are. So we're going to have 1 minus 2, 1 minus 3 times k1, k2 is equal to 0 and 2. So we're going to get k1 plus k2 is equal to 0, minus 2k1 minus 3k2 is equal to 2. So if we do R2 is equal to R2 plus 2R1, we're going to get 2, 2, 0, minus 2, minus 3, 2. So then we're going to get minus k2 equals 2. So k2 is minus 2. So then we have, so then k1 is equal to 2. Okay, so we know what, so our solution is y of t is equal to 2e to the minus 2t so this is our vector solution, but then I think that y of t is given by 2e to the minus 2t minus 2e to the minus 3t. Oh, wait. Yeah, I think that this is right. Let's check our answer. I think that's right. This is problem 23. Nice. Okay, yeah, you just take the first component. All right, I'm going to skip these three because I feel like these are pretty similar. But these I want to do. I want to do all of these. Okay, so the problem is general solution, phase portrait, solve IVP, and then x of t and y of t graphs. Oh, there'll probably be an IVP problem in here. Okay, I'm gonna walk around the block for a second. Take a small break. All right. Just get into it, I guess. So it should all end up being along 1, 3. So x should approach, or the ratio between, so like, so -2 on x. Wait, what? Wait, let's just double check. If we plug in 0 to this thing, then we get 1/4 times 1/3, or 1/3 minus 9/4. This is t at 0. This is 1 times 1 minus 1. So 1/4 minus 9/4 equals -2. Okay, so this, okay, so I did do it right. The only problem is, how do we draw this graph? All right, let's draw it on the next page. Okay, so we had our y0 is equal to -2, 3, right? And then y of t is given by 1/4 e to the 2t 1/3 minus 9/4 e to the -2t 1 minus 1. So basically it's going to decay on that direction. So y0 is right here. And then so what needs to happen though is that both of these are going to go to infinity. In the very long run, both of these go to infinity. So this is going to start. All right, let's just sample some points. So y of 1 is equal to 1/4 e squared 1/3 minus 9 4e squared. What does that even equal to? I have no idea. Anyways, I think it should go out like this. But if it goes to 0, then it let's see if we can plot this. He's definitely going to ask about this on my quiz, so I got to get this right, dude. Okay, so just say y is equal to 1/4 e to the 2x minus 9/4. Oh, e to the minus 2x. Wait, what? Right, so if we just plotted 1/4 e y is 1/4 e to the 2t minus 9/4 e to the minus 2t. Then yeah, this goes away and this dominates, so this is not right. Okay. So then for y though, y is equal to 1 is equal to 3/4 e to the 2t minus 9 plus 9/4 e to the minus 2t. So this goes up 2. And what we should expect to see is that the ratio that y should always be, so it's also plot 3/4 plus. What? I mean, yeah, it's right, but it's also so weird. How was I supposed to know that? Okay, so the actual graph is like this. All right. Ah. Oh, it's 11/4. It's not 9/4. It's 11/4. Okay, whatever. But I'll agree that sketching the x of t and y of t graphs are super important. You know what? It might be easier to just use the face portrait. Because if we're at, what is it, 2 minus 3? No, we're at minus 2, 3. Ah, so it does dip. Okay, cool. Yeah, so the real solution to plotting, so this ChatGPT is giving a bad answer because what you really want to do is you want to use the face portrait to make the x of t and y of t graphs. That is a much better way of doing it. Bruh. Bruh. Okay. Let's get back to work. Next problem. This is going to be problem 28. Alright, so we find the trace equal to 7. Determinant equal to 12 minus 2 equal to 10. Okay, so then lambda is equal to minus 7. Wait, no. 7 plus or minus the square root of 49 minus 40 over 2 is equal to 7 plus or minus 3 over 2 is equal to 10 over 2, 4 over 2, 5 and 2. So they're both positive, so we have a source. Okay, now we're going to find a minus 5i. Okay, so our eigenvector is going to be the solutions to minus x is, 2y is equal to x. So then we have 2, 1. Okay, now a minus 2i is equal to 2, 2, 1, 1. So then y equals minus x. So we have 1 minus 1 equal to v2, v1. Okay, I will be back in a second. wait, 0, 0, 1 right here. So 0, 1. So x is 0, x is 0. Oh wait, actually, because, so actually this is going to be like this. They cross. This is y of t. X of t. Eventually, whoa. Yeah, so in a better picture would be, you know, okay, 29. Let's do problem 29. All right, so we want to then, we're just doing the same thing over and over again, but we're going to find the trace, which is 0, and the determinant is going to be minus 4 minus 6, which is equal to 2. So then we're going to have lambda is equal to 0 plus or minus the square root of 0 minus 8 over 2, which is equal to plus or minus square root 2. Or wait, square root of 2i. Okay, so we have a center. So we now need to figure out what the eigenvectors are. Okay, so a minus root 2i is equal to minus 2 minus root 2i, 3 minus 2, 2 minus square root 2i. Now we solve this equal to 0, so we're going to get minus 2 minus root 2I times x plus 3y is equal to 0. So how do we solve this, right? Because we need to solve this to get the eigenvectors. So, but then we also have minus 2x plus 2y minus y root 2I. So we could do this. We could say y is equal to 1/3 minus 1/3 minus root 2 thirds x. Then no wait. Dude, I hate these complex number ones. These complex number ones are so annoying. Wait, test? Okay, that should be better. So I don't. Because this should probably go away, right? So you get 4x plus 2 root 2, or minus 2 root 2 x. So then we get plus 2/3 x root 2I is equal to 0. I mean, does it really take this much algebra? I feel like I don't know how to do this. I hate the complex ones. The complex ones are so stupid. It's just like, oh yeah, you don't actually have to like do the whole thing. You can just like do that. Okay. Okay. Oh wait. The good news is that we can find solutions to linear system with a complex eigenvalues. The bad news is that these solutions involve complex numbers. We now use the fact that we are dealing with a linear system to find the required real solutions. Okay. Let's get back to it. So the step now is find. Okay, so what have we done? We have an eigenvector and an eigenvalue. So we can form one solution. Y1 of t is given by e to the root 2I t times 2 plus root 2I. Now what we do is we turn this into cos root 2t plus I sine root 2t. Going to be equal to 3 cos root 2t plus 3I sine . Oh shit, this one's going to be 2 cos root 2t plus . Dude, these are the worst problems because there's so much writing. Okay, but we did it. We split it up. And outside of all this is e to the root 2it. Okay, so y re Okay. So then we can let y of t be equal to k1 Okay, and now so this is 0 cos 0, so we get 3. This is 1, so we get 2. Wait a minute, hold on. How did they get 5/3, not 10/3? Oh god, this shit is so crazy, bro. How is it 5/3? I don't even trust that. K1. Alright, so we got the general solution right. Oh, we need to know how to draw phase portraits. I actually don't know how to draw the phase portrait. If we evaluate A times 1, 0, we're going to get -2, 3, -2, 2 times 1, 0 is equal to -2, -2. So it's going to be pointing this way. Oh, because we divided. This √2 is down here. So then you multiply both sides by √2, and you get 10 √2 over 6, which is equal to 5 over 3 √2. Okay. That's K2. Dude, the complex valued ones are brutal. Brutal. Why don't we just do this? Minus 3 minus... Oh, wait. Plus, minus. We're going to just take the plus. See, that's where I was getting confused. Minus 1 plus 2I root 2. 6. This is going to be plus 1, so minus 2 minus 2I root 2. Okay, so then they say you can just assume that these are redundant equations. I don't know how, but you can. So then you get minus 2 minus... Okay, so we have the first eigenvector. Now we just need to... What's y0? Y0 is minus 7. Okay, and then we found that V1 is equal to 3, 1 plus I root 2 for lambda equal to... Oh, I think I messed this up. Or did I? I don't think I did. So it's going to be lambda is minus 1 plus 2I root 2. Okay, so now we have to do this whole thing where, what do we have to do? We have to find one solution. And one solution is going to be y1 t is equal to e to the minus 1 plus 2I root 2 times v1. So this is going to be equal to e to the minus, times t. E to the minus t times cos 2 root 2t plus I sine 2 root 2t times v1. And then we needed to do this expansion, which stinks, so let's just do that here. 3, 1 plus I root 2. So we're going to get 3 Okay, so the top one is the easy one. The hard one is the bottom one. I mean, it's not hard, it's just like brutal to do. The bottom becomes cos 2 root 2t minus root 2 sine 2 root 2t plus, let's not do that, plus I root 2 cos 2 root 2t plus I sine 2 root 2t. Okay, so now our general solution, so y re of t is going to be equal to e to the minus t times 3 cos 2 root 2t, and then on the bottom we're going to get cos 2 root 2t minus root 2 sine 2 root 2t, and then ym is equal to e to the minus t um, 3 sine 2 root 2t, and then here is root 2 cos 2 root 2t plus sine 2 root 2t. Okay, now our general solution is going to be y of t is equal to k1 y re t plus k2 y m t. Okay, then y re of 0 is going to be equal to, so e to the 0, so this goes to 1, so it's just going to be 3 times 1, so this is 3, then this is going to be 1, and this is going to 0, so we get 1. Then ym of 0 is equal to 0 root 2. Now we want to find the solutions for (3, 0, 1) root 2 k1 k2 is equal to minus 7 7. So k1 is equal to minus 7 over 3. It's nice that we have a 0 here. Then minus 7 thirds plus root 2 k2 is equal to 21 thirds. So then we get root 2 k2 is equal to 28 over 3. So then this becomes k2 equal to 28 over 3 root 2 times root 2 root 2. And we get 28, or let's say 2 times 14. So we're going to get 14 root 2 over 6. So then our general solution becomes y of t is equal to minus 7 thirds y re of t plus 14 root 2 over 3 of ym of t. All right, so I think that we have the general solution, but we need to plot the phase portrait. So what I want to do is just get minus 3, 6, minus 2, 1 times 1, 0. This is going to be minus 3, minus 2. So when we plot this thing, first thing we want to check is that our eigenvalue has negative real part. Lambda is equal to minus 1 plus 2I root 2. So this is going to spiral in. So that's the phase portrait. So we have the initial value problem, we have the general solution, we have the phase portrait. Is there anything else? We need to plot the x of t and y of t graphs. So we started at minus 7, 7. So this thing is going to come around like this. Okay, so what we're trying to do is find the x of t and y. So x is going to start at minus 7. So this is x down here, and y is going to be here. And now we should just see something like this. Kind of. And then here, let's see, so when y is 0, let's say when x is 0, y is positive. Then when x is 0, when y is 0, x is high. All right, how many are left? I do want to do, even though I hate them, I do want to grind the complex ones. And I also want to do more of the special case 3.5 stuff. So I'm going to do 3.4, 3.5, and then I'll probably end the stream and I'll go do some other homework. All right, come on. Let's just do these last two. They're not even hard. Let's just hope they're not complex. The complex ones are brutal. All right, problem 31. A is equal to minus 3, 1, minus 1, minus 1. Y 0 is equal to minus 3, 1. Okay, so now let's find the eigenvalues. So trace is equal to minus 4. Determinant is equal to 3 plus 1 is equal to 4. So then lambda is equal to minus 4 plus or minus the square root of 16 minus 9 over 2, which is, what is this? 7? So we get lambda is equal to minus 4 plus or minus square root of 7 over 2. What a terrible eigenvalue. In any case, though, minus 4, or 4 is greater than square root of 7, so then they're both positive. So both positive source, therefore source but you really don't want to find these eigenvalues, or vectors. So anyways, are we sure we did this right? So this is minus 4. Then we're going to get 3 plus 1, 4. Wait, what am I doing? What? 16, what am I doing, bro? Yeah, this is all wrong. I'm trying to rush myself. Lambda is equal to minus 4 plus or minus the square root of 16 minus 4 times 4. Ah, much better. Yeah, they would never give me something so silly as that. So then we're going to get, this goes to 0, and we're going to get minus 2. So we get a repeated negative. So we have like this type of behavior kind of thing where like, this type of thing. I don't know what the eigenvector is, but it's like this type of thing. All right, so now that we have minus 2 equals lambda, we can do a plus 2I is equal to minus 1, 1, minus 1, 1. So x equals y. Oh, I was dead on. Bro, how did I guess that? I just knew it, bro. I just knew that this was the eigenvector. So this is actually a correct face portrait. That's so funny. How did that happen? All right, so that is the face portrait. So now we need to find the general solution, right? So the general, okay. All right, so we have, so V1 is equal to, but let's try to do it so okay, all right. V1 is 1, 1, right? But we want to do this thing where since repeated root, the general solution is y of t is equal to e to the lambda t v0 plus te to the lambda t v1, where v1 is, but this is the way they want you to do it, though. They want you to do this thing where it's like v0 equals x0, y0. And then how do you do this again? I think you have to do this whole thing of like y prime equals a y. But then you also have to take the derivative of this thing. So then you get, all right, so y prime is equal to, this is going to be lambda e to the lambda t v0 plus lambda e, oh wait, e to the lambda t v1, because you take the derivative here, then you just get this, plus lambda t e to the lambda t v1. And then you get this thing where a of e to the lambda t v0 plus e to the te to the lambda t v1 is equal to e to the lambda t a v0 plus te to the lambda t a v1 is equal to this whole thing. And you get these equations. You get te to the lambda t av1 is equal to lambda te to the lambda t v1. This cancels with this, and we get a v1 is equal to lambda v1. So lambda, or v1 0 or eigenvec. I'm going to have to do this every time. I just know it. I'm not going to be able to derive this thing. All right, I'm not going to be able to memorize this thing. So then, but the other part of this is lambda is e to the lambda t a v0 is equal to this part of it, which is e to the lambda t lambda v0 plus v1. And we cancel these, and then we get a v0 is equal to a v0 minus lambda v0 is equal to v1. And then we get this a minus lambda I times v0 is equal to v1. Okay, so then, and I guess this is this other thing of like, for eigenval lambda, a minus lambda I equal to n is nilpotent index 2. And if it's nilpotent with index 2, that means that whatever you apply it to is going to be an eigenvector, because the eigenvectors of n, or the eigenvectors of A are the null space of n. So anyways, but then what we do is we just take, oh wait, did I do this wrong? I think I did this wrong. Because we solve for v1, I thought. Hold on, we got to go back to the textbook again. Oh no, it is this, but then what do? You solve for... But I thought you had to do a linear solve. You don't, though. Okay, so then if we just take a minus, then we're going to get minus 1, 1, 1 times x0, y0 is equal to x0 minus y0. Oh, wait, minus x0 plus y0 minus x0 plus y0. Yeah, these problems are so weird to me because it's like, why don't we just find the eigenvector? Anyways, the general solution, y of t, is going to be equal to e to the lambda. What is lambda? Lambda is minus 2. E to the minus 2t times x0, y0. Plus te to the minus 2t times, and then what is our eigen? It's just going to be like, I mean, I think a 1, 1 goes there, but there needs to be a, but I don't know if it's like x0 here or what. All right, we need to look at the answer. Oh, so they actually literally just put this in here. So it's like y0 minus x0, y0 minus x0. So you can just do that. All right, so this is the general solution. But now we got to get a picture of the phase portrait. Oh, but this is the phase portrait. Oh, wait. This is not the phase portrait. It's almost the phase portrait, but you have to, before you draw the phase portrait, you need to sample a point to get an idea of what the direction is. So if we took minus 3, 1, minus 1, minus 1, 1, 0 is equal to minus 3, minus 1. So it's actually going this way, so it's going to come in like this. Okay, so it's the other way. It's flipped. The spiral goes the other way. Oh, but then we need to do x of t and y of t graphs. Okay, so actually, I think I'm going to eat some food because it's getting late and I don't want to be... Okay. Okay, wait, this is like the last one. So let's just hurry this up. So... Oh, but we didn't solve for the initial condition. Okay, wait. So we're going to just start off with A... This is 31 is equal to minus 3, 1, minus 1, minus 1. Y of 0 is equal to minus 3, 1. We have lambda is equal to minus 2, and V1 is equal to 1, 1. So this helps us. This is repeated. And then our phase portrait looks like this. Okay, now we need to solve. So in our general solution, it was y of t is equal to e to the minus 2t times x0, y0 plus te to the minus 2t times y0 minus x0, y0 minus x0. And then so we need to plug. So first off, we need to, well, what's nice about these is that we know that the IVP solution is just y of t is equal to e to the minus 2t minus 3, 1, plus te to the minus 2t, 1 plus 4 and 4. So I forget, we need to remember that, like, this ends up dominating. But let's just say we're like 1, 2, 3, 1. So we're like right here. So y is going to increase. So y starts out positive, and it kind of, this is like y of t. Oh wait, but how did they solve the IVP? 31. When they plugged this in, they got, oh, this is what they did. They got e to the minus 2t times 4t minus 3, 4t plus 1. This is the IVP. Okay. And then x starts out kind of negative, like down here. And x kind of goes up and above 0. Probably something like this. So this is x t, and this is y of t. And this is time. So it actually comes up faster than that. It comes up like this. All right, was that the last one? There's one more, right? Okay, 32. A is equal to 0, 1, minus 2, minus 3. Y 0 is equal to 0, 3. Okay, trace is equal to minus 3. Determinant is equal to 2. So then we get lambda is equal to minus 3 plus or minus the square root of 9 minus 8, 4 times this, over 2 is equal to minus 3 plus or minus 1 over 2, which is equal to minus 4 over, wait, minus 2 over 2 and minus 4 over 2, which is equal to, lambda is equal to minus 1 minus 2. All right, so sync. All right, now we can just do a plus I is equal to 1, 1, minus 2, minus 2. So we get y equals minus x. So then we have 1 minus 1 is our v1. And then a plus 2I is equal to 2, 1, minus 2, minus 1. So then we get 2, y is equal to minus 2x. So then we get 1 minus 2 as our second eigenvector. So then we can plot our phase portrait. And we have 1 minus 1, which is coming this way. And then we have 1 minus 2, which is going this way. V2, V1. And then they're both negative, so they're both coming in like this. But which is coming faster? This is faster. Faster. All right, so this is the faster eigen. So what does that mean? I hate this extra line that I accidentally made. Okay, so our phase portrait is going to be like certainly things like this are going to be coming in, you know. But which is faster? So if I'm over here, here, let's plot it with Desmos. So what is the, okay, so, all right, so this is going to be, yeah, that's actually correct. Then we just need minus 2x minus 3y. Ah. It always thinks it can do the decays faster. So the faster direction, so it's actually going to be like this kind of thing. All right, let's look at the, because we should have one going this way, and then we should also have one this way, but it doesn't even look like it is. 0, 1. So it does actually get pulled like that. Okay. Yeah. They do actually wrap around. Okay. Now we find the general solution. So my drawing is terrible, but that's fine. So this is V2. Now we want to just, since we have two real eigenvalues, y of t is going to be our easy case, where k1 e to the minus t1 minus 1 plus k2 e to the minus 2t 1 minus 2. All right, then we just need to do our classic, what's our initial condition? So now we need 1 minus 1, 1 minus 2 times k1, k2 is equal to the initial condition, which is 0, 3. So now we can just, we actually add these together and we get 0 minus 1, or 3. So k2 is equal to minus 3. So then if you have k1 minus 3 is equal to 0, k2, or k1 is equal to 3. So then our particular solution is y of t is equal to 3e to the minus t 1 minus 1 plus minus 3e to the minus 2t 1 minus 2. And then we need the x of t. So, okay, so this drawing is freaking awful. But, if our initial condition is 0, 3, then we're going to expect like this type of thing. Because this is gonna decay really fast, right? So shouldn't it try to get pulled by the slow direction? All right, so x starts at 0, and it probably goes up just slightly, and then it comes to 0, asymptotically. And then y is at like 3, and y kind of just comes down. But does it cross it? That's the question, is does it cross? I could see it cross a little bit. So it goes like this. Okay. Let's see if I was right. Yeah, so, okay, so y goes negative. All right, that's it. All right, I'll probably start, after I make some food, probably start up the stream again to do, let's see, it's 3 p.m. I have like 3.5 hours. I'll probably work on my speech next, and then we'll do Laplace transform stuff. Peace out.